My name is Ritesh Pandey, and in this class, this video, we'll talk about a very popular reaction of unsaturated hydrocarbons. We'll talk about ozonolysis, a very important reaction because it will help me in finding the point of unsaturation and thereby the structure of the alkene. There are so many questions where it could be a small part of a big problem. Otherwise, there are questions on ozonolysis only. As the name suggests, ozonolysis, lysis means breaking. We use ozone to find the point of unsaturation, and from the study of the products, we can easily deduce the nature of or the structure of the alkene. Simple to understand, very scoring topic, a topic where there's not too much of chemistry but some basic aptitude required. Let's begin with the smallest alkene, the 2-carbon ethene, and see how ozonolysis will help me in finding the structure of various unsaturated hydrocarbons. So when it comes to ethene, the 2-carbon CH2 double bond CH2, this is how it's made to react with ozone. And you'll notice the way we draw the ozonide O3 with ethene or an unsaturated compound. You place an oxygen between the 2 carbon atoms sharing the pi bond and other 2 oxygen atoms on the head of these 2 carbon atoms sharing the pi bond. This is the ozonide, this is the addition product, this is the ozonide. It's preceded by another molecule which is called a molozonide, and some molecular rearrangements leads to ozonide, the first stable addition product. We'll begin from ozonide, we'll talk about molozonide and what happens before ozonide when the time is right. But we'll take this as the first stable compound, and then when this is hydrolyzed, you want to break it from left and right in this manner, and naturally you will get fragments, you will get mixture of carbonyls. From ethene you will get the left fragment as HCHO, the right fragment as HCHO. So this might give you 2 moles of the same compound, which is formaldehyde, this being a symmetrical alkene. The higher homolo, say propene, and this time when you draw the similar ozonide, you will want to notice again, I'll keep one oxygen between the 2 carbon atoms sharing the pi bond. So I'll keep an oxygen here and the other 2 oxygen atoms on the head of the 2 carbon atoms sharing the pi bond. Again, I'll want to break it from left and from right. And this time, I'll get a mixture of 2 different carbonyls. Because this is not symmetrical, the left fragment will be CH3CHO, the left fragment will be CH3CHO, the right fragment will be HCHO. So this time I'll get a mixture of ethanol and methanol, their IUPAC names, ethanol and methanol, popularly called acetaldehyde formaldehyde. Now from the products, if suppose I remove these 2 oxygen atoms, if I remove these 2 oxygen atoms, I get CH3 CH double bond CH2. So from the mixture of carbonyls, I can easily deduce the structure of the alkene, which is CH3 CH double bond CH2. When it's a symmetrical alkene, you might get 2 moles of the same compound. I can again place 2 formaldehyde in this manner. Remove these 2 oxygen atoms and get CH2 double bond CH2. So this is how from the ozonolysis products I can easily deduce the structure of the alkene. It's important that you quickly learn how to draw the ozonide, which is placing an oxygen between the carbon atoms and the other 2 oxygen atoms on top of the carbon atoms sharing the pi bond. Very quickly we're going to learn how to draw the ozonide, and certainly if in a problem the products are given, I want to place the 2 compounds next to each other, remove the couple of oxygen atoms and get the point of unsaturation. We want to see this for some more alkene. So let's move to the 2 forms of butene, but1ene and but2ene. So if it's for a 4-carbonate alkene, but1ene and but2ene, naturally I want to write but1ene as CH3, CH2, CH double bond CH2, and this with ozone, this is how I draw the ozonide, CH3, CH2, CH, an oxygen here is CH2 and these 2 oxygen atoms over the carbon atoms which are sharing the pi bond. Now but1ene when the ozonide is broken from left and right, you will get a mixture of two different carbonyls. So you get a mixture of two different carbonyls, which are CH3, CH2, CHO and HCHO. Certainly, when you remove these two oxygen atoms, CH3, CH2, CH double bond CH2 is how you get the structure of the ozonyl alkene. If it's but2ene, which is a symmetrical alkene, now the ozonide might look like the following. It might look like this following. This is how I draw it. One oxygen, between the carbon atoms sharing the pi bond. Two above the head of these two carbon atoms. And this being symmetrical, and again this being symmetrical, this will give you ethanol as the left fragment and the right fragment. You might get 2 moles of the same compound, which is ethanol. Now yet again, keeping two ethanol next to each other, I can have the oxygen removed and arrive at the structure of CH3, CH double bond CH3, which is but2ene. So but1ene will give me a mixture of 3 carbon compound and 1 carbon compound, which is propanol and ethanol. But2ene will give me 2 moles of the same compound, 2 carbon compound, which is ethanol. And this also happens to be a very popular way of differentiating but1ene and but2ene. Deducing the structure, the position of pi bond, whether it's but1ene or but2ene. One important fact is, while hydrolyzing it, you always keep zinc around. See the left fragment, this becomes CHO, right fragment, this becomes CHO. What happens to this oxygen at the center? This oxygen with water will form peroxide, Peroxide is a strong oxidizing agent and it can oxidize aldehydes to a mixture of acids. If you want to get aldehydes, if you want to get a mixture of carbonyls, you will have to keep zinc around. Zinc will neutralize this oxygen and H2O2. You will want to keep zinc around. Zinc will neutralize this oxygen or H2O2 and prevent the oxidation of aldehyde to acid. So zinc is required to get aldehydes and not acids. And in the common ozonolysis using zinc, the process is called reductive ozonolysis. So common ozonolysis is reductive ozonolysis, where we want a mixture of aldehydes only. In absence of zinc, aldehydes will become acids. Let's talk about a few more cases. Say if it's a 5 carbon compound. And we might stop drawing carbon hydrogen every time. We might want to go to the bond line form. So say we have pent1ene, 1, 2, 3, 4, 5, pent1ene. The ozonide will look like this. And if it is pent2ene, naturally the ozonide will look like this. Now certainly pent1ene, and if the ozonide is broken from left and right, it will give you a 4 carbon fragment and 1 carbon fragment. Remember, in presence of zinc, because you want aldehyde, so this will give you CH3, CH2, CHO, and 1 mole of formaldehyde, HCHO. Now you remove these two oxygen atoms, and when you remove these two oxygen atoms, you get CH3, CH2, CH double bond CH2, which is the structure of pent1ene. Doing the same for pent2ene ozonide, to break it from left and right, you get a 3 carbon fragment and a 2 carbon fragment. So naturally, this time reductive ozonolysis using zinc and the hydrolysis of the ozonoid will give you a 3 carbon fragment. It will give you a 3 carbon fragment, which suppose is propanol, and now this is ethanol. From the right you get ethanol. From the right you get ethanol. So when you get ethanol here, you remove these 2 oxygen atoms. And this will give you the skeleton of CH3, CH2, CH double bond, CH3, which certainly is the structure of pen-2-ene. So this will tell you about the corresponding alkene being pen-2-ene. If the ozonolysis product is a mixture of propanol and ethanol, it must have come from pen-2-ene. And if the ozonolysis product was butanol and formaldehyde, it must have been pen-1-ene. In due course, you get used to it to the extent that if it's not there for the school board exams, you can do away with writing the ozonoid, and very easily you might want to cleave it this way, you might want to break it this way and see a 4 carbon 1 carbon fragment or a 3 carbon 2 carbon fragment. But to begin with, you will want to learn how to draw the ozonoid, and in due course you will realize that this is going to be such an important way, such an important tool of establishing the formulae of so many unknown hydrocarbons in the past. So we'll want to take up a few more cases. Maybe some alkenes which are furthermore branched, and say we talk about tri-substituted alkene. So it could be an alkene like this one, 2-methylpropene, or it could be an alkene like this one, 2-methylbutyene. Naturally, by this time you would have realized that this will give you a 1,2,3 fragment ketone and a 1 fragment aldehyde, and this might give you a 3 carbon ketone and a 2 carbon aldehyde. We'll just want to keep on drawing the ozonoid till we are very comfortable with it, and naturally this is going to give me acetone and formaldehyde. Now obviously when it gives me acetone and formaldehyde, I can write them next to each other. I can remove the 2 oxygen atoms and arrive at the structure of the ozonyl alkene. Similarly for this compound, I can predict it's going to be acetone and ethanol, but we'll keep on drawing the ozonoid. Till we are absolutely comfortable with it. If this is the ozonoid, we'll want to break it from left and from right, and naturally it will give you a 3 carbon ketone acetone and CH3CHO. All the while you want ethanol and not acid, so you'll want to keep zinc around. All are cases of reductive ozonolysis. So in due course you get used to it. From the very look of the alkene, you can predict the nature of the carbonyls, and certainly from the nature of the carbonyls, you can predict the structure of the alkene. But we'll want to take up more cases. We'll want to take up cases where alkene is furthermore substituted. Then we'll want to take up cases of polyenes where there are more than 1 pi bonds. Now certainly, if it's tetra-substituted, if an alkene is tetra-substituted, which means, say it bears a look like this. Say if it's a compound like 2,3-dimethylbutyrene. Now some of you would start predicting that this will give me 2 moles of acetone, this will give me 2 moles of acetone, this will give me 2 moles of acetone, and certainly we will want to practice it for a little while and then start drawing in this manner. This from left and right. If hydrolyzed, will give me acetone from left, acetone from right. So this is how it's going to be. You bring the 2 oxygen atoms close to each other, you remove the 2 oxygen atoms, you get back to the structure of the ozonyl alkene. And as I told you, it's going to become instinctive with time. You practice a few times and then you'll be good at it. Certainly, in general, this can be represented like R1, R2, R3, R4 on ozonolysis, and then hydrolysis by zinc, giving me two carbonyls which are going to look like R1, R2 double bond O plus R3, R4 double bond O. If all the four are hydrogen, it becomes ethene. If all the four are hydrogen, it becomes ethene. And naturally, with all hydrogen, it will give you a mixture of 2 moles of formaldehyde. And if all are alkyl groups, if all are methyl groups, like this particular case, it will give you a mixture of 2 ketones. If it's symmetrical, it will give you 2 moles of the same compound. We're going to take up cases now where there is more than one pi bond. We're going to take up cases involving more than one pi bond. We'll talk about diene, triene, then we'll talk about cycloalkene, and every time we'll want to learn how to draw the ozonide. We'll keep it simple and we'll break it properly from left and right. So let's talk about what if you have polyenes, dienes, trienes. If you have dienes, trienes. Now the simplest diene which comes to mind is buta 1,3 diene, on ozonolysis. This is how you draw the ozonide. This is how you start drawing the ozonide. Place an oxygen here. Break it from left, right, and naturally this time, because there are 2 pi bonds, buta 1,3 diene. Let's write it, buta 1,3 diene. Because there are 2 pi bonds and a diozonide form, it will give you 3 fragments. One to the left, another to the right, and one in the center. Now the one to the left is certainly a 1 carbon fragment formaldehyde. The one to the right is certainly another 1 carbon fragment, which is HCHO, and in between you have CHO. So this is what you have to keep in mind. If it's a polyene, it might give you dicarbonyl, and you'll want to place this always between these two. So when you are going to find the structure of the original alkene, you will want to place the dicarbonyl in between so that all the oxygen atoms can be removed like this. And it will give you CH double bond CH2, and the structure of buta 1,3 diene will be arrived at. It's a conjugated diene, double, single, double. We can talk about maybe along the chain. We can talk about 1, 2, 3, 4, 5, 6. Say hexa 1,3 diene. We can talk about hexa 1,4 diene. 1, 2, 3, 4, 5, 6. I'm naming it hexa 1,4 diene. And yet, what I do is I draw the ozonide, the diozonide. How I draw the ozonide is an oxygen here, a couple of oxygen atoms here, and then between these 2 carbon atoms an oxygen here and a couple of oxygen atoms here. Now I break it from left, and right. You're taking like 3 fragments, one to the left, one to the right, and one at the center. Now the fragment to the left has to be a 1 carbon fragment, which is formaldehyde, methanol. So I'll write methanol somewhere here, HCHO. The fragment to the right is CH3CHO. So I'll naturally write CH3CHO somewhere here. And when it comes to the middle fragment, it's CHO, CH2CHO. Propane 1,3 diol. It was glyoxylethane 1,2 diol here. Here you have a 3 carbon fragment. So we'll want to write it like CHO, CH2CHO. And see, you will always want to keep the dicarbonyl in between so that you can comfortably remove these oxygen atoms. And certainly you will arrive at the structure of 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4. So hexa 1, 4. 1 and 4. Hexa 1, 4 diene can be arrived at by properly aligning the ozonolysis products, where you know that the dicarbonyl must have come from polyene, and you want to keep on writing the dicarbonyl compound in the middle. It will help you in arriving at the structure of a diene or a triene. Another way, another case where you can get dicarbonyl is if you are dealing with cycloalkene. If you are dealing with cycloalkene, you will want to keep copying this at your convenience. You will want to keep copying this at your convenience, and at some point of time, all this can be done with more authority, with more confidence, and so many times merely by looking at the compound, merely by looking at the compounds. So if we had done till say 10, 11, if it's compound 12, and I am given cyclohexene, now naturally I can kind of predict, I can count of predict that this will give me CHO, CH2, 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 CHO. So this will give me hexane, this will give me hexane 1,6-diol, it can give me hexane 1,6-diol. Obviously, I can confirm this, by drawing the corresponding ozonide, there's an oxygen here, couple of oxygen atoms here, break it from top and bottom. So CHO, CH2, 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 CHO. But it's only about time, you get so good at it that from the look of the compound, you know it's going to be hexane 1,6-diol. Next, what's required is, when you have to convert it to the original alkene, you will want to just remove these two oxygen atoms and place a pi bond here, If it's a case like a 5-membered ring, cyclopentene with a methyl group here, and most of you can now predict it's going to be an acetone group here and an aldehyde group here. You will want to name the product 1, 2, 3, 4, 5, maybe 5 keto or 5 oxo, 5 keto or 5 oxo pentanol, 1, 2, 3, 4, 5, 6 hexanol, and this is going to be the product. This is going to be the product. CHO here and double bond O here. Naturally, if you bring these two oxygen atoms close to each other, place a pi bond here, you will get the structure of the original alkene. And if you still want to keep on drawing, the ozonide, simple, you will want to place an oxygen here, couple of oxygen atoms here, break it from left and right, CH3, C double bond O, CH2, 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 CH2. So say both compound A and B, have the same formula, both are like C6H10. A C6H10 which gives you hexane 1,6-diol, and ozonolysis product must be cyclohexene, and a C6H10 which gives you 1, 2, 3, 4, 5 oxo or 5 keto hexanol 1, 2, 3, 4, 5, 6, yes, 5 keto or 5 oxo hexanol, a compound which gives you 5 keto hexanol is the ozonolysis product, must certainly be this compound, which is 1-methyl cyclopentene. I want to draw maybe one more compound with the same formula, and get a different ozonolysis product. So with C6H10, a 6-membered ring, a 5-membered ring, suppose I get a product which is 2,5 hexane dione. If suppose I have another compound, and the ozonolysis product is 2,5 hexane dione. Now I know how to draw 2,5 hexane dione. It will be drawn like 1, 2, 3, 4, 5, 6. And from this compound, I can draw the original alkene. I'll remove these two oxygen atoms. I'll draw the original compound C in this way. So now you can approach the problem from either ends. You're given a compound, you can draw its ozonolysis product. You're given the ozonolysis product, you can draw the original compound. Here you'll have to bring the two oxygen atoms close to each other, remove this, place a pi bond, and naturally to go from this end to this end, which is ozonolysis, zinc H2O, you'll know how to draw the ozonide. Naturally, you'll want to keep an oxygen here, an oxygen here, an oxygen here, and break it in this way. So CH3, CO double bond O, CH2, CH2, C double bond O, CH3. So I think while drawing these many structures, you'll definitely get a hang of dealing with the ozonide, getting the final product, and from the look of the final product, reducing the structure of the original alkene. Now all the three compounds A, B, C had the same formula C6H10, the same degree of unsaturation, one for the ring and one for the pi bond. But based upon their ozonolysis product, I could deduce the structure as cyclohexene or methyl cyclopentene or certainly 1,2 dimethyl cyclobutane. It would become just a little bit tricky if it's a ring containing more than one pi bond. It might become just a little tricky with a ring containing more than one pi bond. And let's talk about a very popular compound, which is benzene. Let's talk about benzene. And it's a fact. Faraday discovered benzene. Tickule gave a particular structure of benzene. The formula of benzene was known. As C6H6. Degree of unsaturation was known. And this was one possibility. Which we know is the reality now. And certainly, Tickule could confirm this as the structure of alkene, benzene, with a 6-membered ring and 3 alternate pi bonds. Because this on ozonolysis followed by hydration is going to give me 3 moles of glyoxal. Some of you might just want to confirm it this way. CHO. And others might want to do it in a more elaborate manner. And that manner is drawing the triozonide. So there is an ozonide here, and there is an ozonide here. A benzene would certainly react with 3 moles of ozone this way, giving you a triozonide. You break it from left and right, and this time you will get CHO, which is 3 moles of CHO, 3 moles of glyoxal. Certainly they can be oriented in a particular manner to get a 6-membered ring. I'm avoiding to do that. And because it appears to be a very student-friendly topic with very little chemistry involved, I told you in the beginning, so many times you become a little complacent with this topic. So you'll want to show that much of maturity. You'll just not want to get carried away with an easy problem based on ozonolysis, because there could be some tricky situations. You're going to find some questions in my problem sheet where you'll have to be a little more careful. But other than that, it's a simple case. You draw the ozonide, you confirm the ozonolysis product, and this is how the structure of benzene was concluded to be a 6-membered ring with 3 alternate pi bonds. It was concluded as a 6-membered ring with 3 alternate pi bonds. A very popular question which came in one of these exams, allow me to wrap this. A very popular question which came in one of these exams was about an aromatic compound which is called xylene. Say you have this ring with one methyl group, and it's called toluene. With another methyl group, it's called xylene, and if they are next to each other separating 60 degrees, naturally it's the orthoisomer, and you'll want to call it orthoxylene. Now orthoxylene on ozonolysis, which is reductive, different types of products. It came in a real life exam. It was a real nice problem. different types of products. Now, so many people who would have drawn a structure of orthoxylene like this would have come up with the ozonide, broken it in this way, and maybe thought of a CH3COCHO, CH3COCHO, and CHOCHO. So, if you have got a hang of drawing these structures, now you'll see there will be CH3C double bond O CHO, which will be 2 moles of CH3C double bond O CHO. You can call it 2-keto-propanol, you can call it 2-keto or 2-oxopropanol, 2-keto or 2-oxopropanol, and 1 mole of CHOCHO, 1 mole of CHOCHO. And so many people would have thought 2 types of products, and the answer would have been 2 types of products. Now 2 was the wrong answer. 2 was the wrong answer because while thinking of possible structure of orthoxylene, you will have to draw this structure as well as another structure which is the resonating structure of benzene, where this time between these 2 carbon atoms having methyl group there is no pi bond. So this could be an alternate structure. These are 2 resonating structures. One where you have pi bond between the 2 carbon atoms bearing methyl, and another where there is no pi bond between carbon atoms bearing the methyl group. This also is orthoxylene. This is also orthoxylene. And naturally, when you think of cleaving these 3 bonds, you'll get CHO, which is 2 moles of glycol, but this time there will be another fragment which will be CH3C double bond O CH3. You'll get another fragment which is CH3C double bond O CH3. I might call it buta 2,3 dione, and naturally thus the number of possible products is A, B, this is also B because these 2 are same, and C, and the answer to this question is not 2 but 3. But you can think about these 3 products, only if you are being that cautious. You don't get carried away with the nature of the problem, which is ozonolysis, generally a simple topic. And while drawing the products from this structure, you also keep in mind that there is an alternate structure possible, and this was a real nice problem where the number of possible products, ozonolysis products, were 3. It also helps us to conclude that yes, the 3 pi bonds in the 6-membered ring of benzene, they are involved in resonance. These are 2 possible structures possible, and naturally from these 2 possible structures, I can get A, B, and C, 3 different ozonolysis products. So there are going to be some questions which will test your aptitude. Otherwise, it's a very simple topic, very schooling topic. I'm going to leave you with an assignment containing questions which have come in different exams, which will test your understanding of this topic. This much for the time being. In the next video, we'll carry on with more reactions of that. Thank you very much.